And welcome back to another video on strength of materials. In this video, we're going to talk about how we analyze truss structures. So the key concepts you're going to want to know for this is static equilibrium. And again, we talked about this in a previous video, just to go over it again one more time really quickly. Static equilibrium dictates that the sum of the forces in every direction equals 0. So if we're going to do a 2D example, so sum of the forces in the x equals 0, and sum of the forces in the y direction equals 0. And static equilibrium also states that the sum of the moments must be 0 in every direction. And that means the sum of the moments about the x-axis equals 0, sum of the moments about the y-axis equals 0. All right, so we're going to talk about truss analysis through an example. So let me explain what we have going on here. So this is a very simple truss that has 4 members. So here at point A, we have a pin support. Again, in the previous video, I talked about different support conditions. So at A, we have a pin support, which means that there's 0 degrees of freedom at A, or 0 degrees of linear freedom. So it cannot move in the X or Y direction. It's pinned in place. So at this point, we don't have any movement. The truss is stuck here. At point B, we have a roller support. So that means we do have a degree of freedom in this horizontal direction. We can move back and forth in that direction, but we can't move back up and down. So we're limited to 1 degree of freedom. And this is a triangular truss. And these up here are the applied loads. So we have one downward load of P, where P is equal to 35 newtons. Then we have a force to the left acting up here, 2P, so it would be 70 newtons, 2 times 35 here. And those are both acting at point C. So point A is down here at the pin, point B is at this roller support, point C is the top of this truss where the 2 forces are applied, and point D is down here where these 3 members intersect. So when we're doing truss analysis, especially for a materials type problem, our main goal is to find the internal forces. And what I mean by that is the forces inside these beams. So you can imagine maybe this is like the roof of a house maybe, or something like that, and these are all beams that carry all of the weight. So we want to find the force inside each of these beams. And there are a few different ways to do this, but we're going to go through it slowly step by step. So in this example problem, we're given the angles of the triangle. So angle C is this full angle up here. That's equal to 80 degrees. We have angle at point A here, which is equal to 60 degrees. And naturally, we have angle B here equal to 40 degrees. They all sum up to 180, as the interior angles of a triangle always should. And then we also have side A here. This lowercase a symbolizes the line segment from C to B. This B here is the line segment from A to C. And this lowercase c here is the length from A to B. And we're given lowercase c, that's 10 meters. We're not given A, and we're not given lowercase b. Great. So in order to find the internal forces in all of these beams, the first thing we need to know is all the geometric constraints. So all the geometric properties, basically. So we know all the angles, that's given to us. We know what C is, that's also given in the problem right here. So what are we missing? Well, it looks like we're missing A and we're missing B. So we need to use some geometry in order to get A and B. The way we're going to do that is using the law of sines. So let's go through that calculation together. So step 1, use the law of sines to solve for A and B. So I just redrew the triangle we had in the problem here. And now we're going to do a little bit of geometry using law of sines to solve for A here. And we're going to solve for B as well. Great. If you don't remember the law of sines from geometry, it's pretty simple. It essentially says the length of a side of a triangle divided by the sine of the opposite angle. So it has to be the angle opposite. So A divided by sine of theta A, which is the angle opposite, so it'd be this 60 degrees here, is equal to some other side, we could say maybe side B, divided by sine of theta B, which would be this 40 degrees here. So this is the law of sines. The law of sines just says the length of a side divided by its opposite angle is equal to the length of another side of a triangle divided by that side's opposite angle. So we apply it first to find side A here. So A divided by sine of 60, you can see that right over here, is equal to 10, which we know C, this is lowercase c, is equal to 10. That was given in the problem. Divided by its opposite angle, 80 degrees, right? And this is a very simple algebraic equation we can solve here. And then we get that A is equal to 8.79 meters. Great. We do the exact same thing for B. So B is this side. So B divided by its opposite angle, the sine of its opposite angle, 40 degrees, is equal to 10 meters here divided by the sine of its opposite angle, 80 degrees. And then we get that B is equal to 6.53 meters. Great. So now we've used law of sines to find these two sides. The next step, going back to our original problem statement, in order to find these internal forces here, again, that was our original goal, to find the internal forces in all these beams, we need to find the reaction forces at A and B, right? Because if we have these forces, these are external forces here that are being applied, and then we're going to have a reaction force at A here because of the pin support, and a reaction force B here because of the roller support. Since A is a pin support, we're going to have a force in the X and Y direction. So we're going to have some force acting up here. We can call that A sub Y. And we're also going to have some force in the X direction, right? We can call that A sub X. Since B is a roller support, it only has a force in the Y direction, right? There's no force in the horizontal direction. It's free to move this way because there's like little wheels down here. But there is a normal force acting upwards here. We can call that force B. And AY, A sub X over here, and B, these are all reaction forces. Since we have these applied loads here at 2P and P, we're going to have reaction forces at AX, AY, and B. So now we need to use the static equilibrium equations we talked about to solve for AY, AX, and B. So let's jump into it. So here I just drew a free body diagram of the situation as well as some of the geometric constraints that we solved for. I defined our positive x-axis as to the right, our positive y-axis as up, and a positive moment, we'll talk about that in a sec, is counterclockwise. So step 2 is use the equilibrium equations to we for reaction forces. So we have 3 equilibrium equations, right? Sum of the forces equals x equals 0. See that one right here. We can also use sum of the forces in the y direction equals 0. And then we can also use some of the moments about A equals 0. So 3 equations, and our 3 unknowns are AX, AY, and B. So let's first apply this equation in yellow here. Sum of the forces x equals 0. So what are the forces in the x direction? Well, we have an AX here, right? So we have AX, and that's positive because it's to the right. And we also have a 2P to the right, also positive. So AX plus 2P, and those are the only forces in the x direction. So those should sum to 0. That's what we have right here. Now we're solving for AX because we know P is equal to 35 newtons. So we get AX is equal to minus 2P. And we know P is 35. 2 times 35 is 70. So AX is equal to negative 70 newtons. This negative sign here means that AX is actually in the opposite direction that we drew it in this picture. So AX is actually pointing to the left. That's what that negative sign means. Great. That wasn't too bad. Let's now do the moment equation. And this one's a little bit trickier. So we're going to take the moments about point A. So point A, again, is right here. And we want to find the moments about that point. So which forces do you think exert moments? Well, force B here is going to exert a moment, right? And again, we know a moment is sort of similar to a torque, right? A moment is equal to a force times the distance to the axis of rotation. So we're doing moments about point A. So point A is going to be our axis of rotation. So it's going to be the force, it's going to be B, times the distance of the axis of rotation, 10 meters. And again, we remember this 10 meters, I'll just write that as 10 meters here. Great. What other forces exert moments? Well, we have this P that's pushing downward, right? So this B exerts a positive moment, right? Because it causes this to rotate counterclockwise in that direction. This P is a negative moment because it causes rotation in the opposite direction about point A. So the moment due to P, well, we know it's going to be force times the perpendicular distance from where P acts to where A is, right? So it's going to be P, so I'll write that minus P because it's a negative moment, times this distance here, right? And this distance is equal, well, we could look at, this picture's getting a bit messy, but there's a triangle here, right? So if we want to find this distance in light blue, that's just going to equal 6.53 times the cosine of 60 degrees. So it's going to be times 6.53 cosine 60 degrees, right? And that's the moment due to this P here. All right, and there's one more force that exerts a moment. You might have guessed, but that's going to be this 2P here, right? And the moment of this 2P is also going to be negative because it's causing it to rotate in the counterclockwise direction, right? That moment is going to be minus 2P. And then what's the perpendicular distance from where this force acts to the lever arm? Well, this force acts in the x direction. So the lever arm of this force is going to be this distance here in yellow, which is going to be 6.53 times this sine of 60 degrees. 2p times 6.53 meters. Sorry, it's a bit messy. Multiplied by sine 60 degrees. And this is all equal to 0. Right? This equation is pretty messy, but we know P is 35. We don't know what B is, so we have one equation here. Highlight this equation. And we need to solve for B here. So if you go through this algebra, you would add these two terms to the other side and divide by 10. You would end up with B is equal to 51 newtons. 51 newtons. So that's the force exerted by the roller support at point B. Great, we're almost done. Going back to this diagram, what's the one force we haven't solved for? We know AX, we solved for that. That was minus 70 newtons. We know B, that's 51 newtons. But we still need this A sub Y. So what equation do you think we're going to use to get A sub Y? We've already done some of the moments equal 0, some of the forces in the x direction equal 0. Right, we're going to do some of the forces in the y direction equals 0 now. And that's why we're going to solve for A sub Y, because A sub Y acts in the y direction. So sum forces equals y. Again, this comes straight from static equilibrium. This body is not moving, so we use our static equilibrium equations to solve. The sum of the forces y equals 0. And we know up is the positive direction, right? We defined that earlier. Up is positive. So this is our sign convention. Let's go back to our free body diagram and see what forces are acting in the vertical direction. So we have B acting in the vertical direction, and it's acting up. So that's positive. So that's going to be 51 newtons up, 51 newtons upward. That's one of our forces, but we need to sum up all the forces, right? Because we have this sigma here. What are the forces in the y direction? Well, we have this P that acts in the negative y direction, and we know that's 35 newtons. That was given to us in the problem, so it's going to be minus 35. Great. What other forces do we have in the y direction? Well, of course, we have A sub y in the y direction. That's what we're solving for, right? And it looks like that's pointing upwards. So let's say plus A sub y. So plus A sub y. And that's all equal to 0, right? The sum of our forces in the y direction equals 0. Now it's just simple algebra to solve for A sub y. So we add this 35 to the other side, subtract 51. So A sub y equals 35. Adding this to the other side, minus 51. So it's minus 16. So A sub y equals minus 16 newtons. So now we found all our reaction forces, right? We found B, which acts upward, A sub y. Since there's a negative sign here, that means it's going down, right? And we also found A sub x earlier. Great, so now that we have our reaction forces, we can go to our final step, which is finding our internal forces inside of each beam. And that will be the topic of the next video. Thanks for watching and see you next time.